imaging beamline I13-1. So yes, we are 1 minute ahead of schedule. Still, I think everybody's here. So if you're ready, you can start. So thank you.
Okay, thank you very much. And good afternoon, everyone. So my name is Kudakwashe Jakata, and I'm going to give my presentation is largely on tomography, but actually what I've decided to do is to concentrate on imaging techniques, X-ray imaging techniques. So I'll start with tomography and then I'll move on to tachography, which is what we're doing mainly at our beamline these days. Okay, so starting off the fundamentals of synchrotron X-ray imaging techniques. I'm sure quite a lot of the stuff has already been covered in some of the earlier sort of lectures and presentations. So I will try to skip over some of the very basic things that I think have been covered already. Um, so for imaging generally, what you have is you've got an initial intensity of X-rays. So here, for example, in this image, they have got an intensity I naught, so represented by this big red arrow. And so the source of the X-rays, it can be a synchrotron source, but you can also have a lab source. So in a lab source, in most cases, you have a cone beam geometry. So simply because the beam will look like a cone, like a cone. But then also you will not you have polychromatic X-rays, whereas at a synchrotron you have the choice of using polychromatic X-rays, or you can also use a monochromatic beam, where you are making use of a monochromator. So that beam of X-rays, it passes through a material. If let's assume it's homogeneous, so maybe it's an aluminum block, and it's got a thickness X, and afterwards, some of the X-rays are absorbed, and then some are transmitted. And the transmitted X-rays, which is a lower intensity because some of them have been absorbed, is I, and this is represented by the sort of thinner arrow, which is supposed to show that we have a lower intensity of X-rays after passing through the block. So there's the Beer-Lambert law, which sort of explains this. So if for the intensity that we get afterwards, I, is given by I naught, the initial intensity, and e to the power minus mu x, where x is this thickness that we had, and mu is the attenuation coefficient of the material, which it really which depends on the type of material that you have. So that's the equation, of course, that gives you the transmitted X-ray beam intensity. But for a polychromatic beam, then we've got different energies. So then our this equation, we now integrate over the different energies of X-rays intensities as a function of energy, and then again because if we don't always work with homogeneous materials, so we have materials that, like if I pick a rock from outside, it's made up of many different elements and a number of materials. So then we have got different attenuation coefficients, and that will also be a function of the atomic number and the energy. And they have different thicknesses as well, these different materials in the rock. And so we integrate over the different sort of length scales of the material. So the equation ends up looking a little bit more like this. Yeah. So of course the attenuation coefficient then. So because the different materials absorb different amounts of X-rays in a material, what you then notice is that when X-rays pass through a material, and then you put a detector on the other side, what you're going to get is you're going to get a radiograph with different sort of regions of different grayscale, and this difference in grayscale, which we refer to as contrast, is as a result of the differences in the attenuation coefficient. And that attenuation coefficient, what's actually happening when the X-rays are passing through the block is that there's Compton scattering happening, there's pair production, there's Rayleigh scattering, and sort of the different contributions to this depending on the photon energy that you're working with. And so what you then end up with is you get a total attenuation here, and so you can then decide what energy you need to work at depending on this attenuation curve. And sometimes, of course, there are materials where you look at the material uh, and you can see the different materials and the origin of interest. But when you put it into the uh, 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 when you do imaging, you find that you can't see the contrast between the material around it and your region of interest, because the attenuation coefficients are pretty close to each other. Um, so that can lead to that is one of the problems of absorption contrast, because here yeah, we are getting our absorption, we are getting contrast because of the differences in the way that the different materials absorb X-rays as they pass through that material. And so uh, there is then phase contrast imaging, which is one of the main techniques that is used at X-ray synchrotrons, um, because because we have more coherence in X-rays in the X-rays that are produced at synchrotrons. I believe this has already been discussed, so I will not go further into it. But we have more coherence, and we also have higher intensity. So what happens is then here, for example, in this image, you've got your X-ray source, and your X-ray source is producing this sort of this is the wavefront, these X-rays of the X-rays that are produced, and as they travel towards our sample here, which is this red solid sort of object here, and after passing through the sample, what you then observe is that there is a slight deformation of the wavefront. Um, and so when this wavefront is deformed, adjacent waves are partially superimposed and they interfere with one another. And because of this, you start getting this interference at a certain distance from the sample, and that results in us getting a diffraction fringe around the sample. And as you can see in this image, when you're closer to the sample, even though the deformation has already happened, but the interference is not yet observable. So if we were to put your detector here, you would only get the absorption contrast, but you would not get this diffraction fringe. But as you move further away, uh, 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 for example, at this distance here, you're now observing the interference, and that is now resulting uh, in um, in you observing this diffraction fringe. Okay, so generally, if you have an object that has a diameter d, what you notice is that Fresnel diffraction appears when the sample and detector are relatively close to each other. So this is where you are not yet observing the phase contrast effect. So Z here is the distance between the detector and the sample. And of course, D is the diameter of the object, and lambda is your wavelength. And so when this is smaller than this, then you don't observe it. But then Fraunhofer diffraction is generated when the sample and detector are placed considerably apart from one another. Um, and so when when Z is bigger than D squared over lambda, then you start observing this Fraunhofer diffraction. A good example of this is this simulation that's been done So what you notice in figure A, you've got the closed circles, these three circles, and um, the open circles. So the open circles are representing materials that have got a very low attenuation coefficient. So really hard to, or very low absorption, and whereas the closed circles are representing sort of, let's say, spheres that have got very high absorption. So what you notice is at B here in this image, the detector is placed 0 0.1 millimeters away from from the sample. And because of that, we are only observing absorption contrast. And because of that, you only see these three, which have got high attenuation, whereas the other ones, we actually don't observe them. As you move the detector further away, a millimeter away, then what you notice, you start actually seeing all of the samples, including the ones that have got low absorption contrast. This is now because of the phase contrast that we are observing. But as you move even further away, then you start getting this diffraction. Fringes become much stronger, and at 1 millimeter away, and at 10 millimeters, even much stronger. And as you can see at F, you start getting these diffraction patterns. So for phase contrast tomography, then you want to mainly work in this region C, and there is of course a way of calculating, depending on the energy that you're working on, at what distance you need to place your detector so that you can actually observe phase contrast in this region. Then later on, I'm going to move on to talking about tychography. And for tychography, I think you'll be working sort of in this region here. Um, so moving on, so phase contrast, I think one might then ask, what use is it, and is it very important? So here I'm going to show an example of the power of this phase contrast imaging that is possible at light sources. Um, the I think so insects are really hard to image sometimes because they are an example of a sample that would have low absorption contrast. So you might not see anything on your detector. But then there are also insects that existed sort of millions of years ago, and or it's hard for insects to be preserved, but sometimes they're preserved because there is this ember where they get stuck in ember, and over time the ember covers the insect, and it hardens, and over millions of years it becomes rock, but the insect is preserved inside. And so when paleontologists pick this kind of fossil material, if it's transparent, you can actually see the insect inside, but then when you put it in an X-ray beam, then you don't observe anything, this is an example of a radiograph of after placing such a sample in front in an X-ray beam, and acquiring the radiograph. And as you can see, you don't see anything here. You just see that there are some cracks maybe in the amber, but otherwise there's nothing else in here. So this experiment was done by Paul Taffero and colleagues at the ESRF. But then once you then adjust the distance of the sample so that you get phase contrast, this is what you then see. You can actually now see the insects, and there are two of them inside the sample, and you actually see some of the other materials and imperfections in the amber. So this is the power of phase contrast imaging. So of course, at the end of the day, when you're acquiring when you're doing these experiments, you acquire these radiographs, but then you rotate the sample and acquire the next radiograph through 360 degrees or 180 degrees. You acquire something like 3,000 images or so, and then you reconstruct a 3D image of the sample, and then you can then sort of analyze it. So this reconstruction that happens after you have collected the projections, there are several algorithms that are used to reconstruct 3D image, and I I think, for example, the most widely used X-ray reconstruction method is the filtered back projection, or FBP. So back projection it's a processing technique that returns projection data to the sample position along the direction of the X-rays when conducting forward projection through the opposite direction. I'm going to sort of uh, try to explain this a little bit further. So if we imagine if this square here is our sample, and these are the attenuation coefficients, the ones inside inside the boxes, and so and our sample has got a, a a material with a very high attenuation coefficient in the center of 10. So we take projections as we rotate the sample. So for example, when the sample is oriented this way, our X-rays are passing through this from below the page going up. And so what we're going to see is if we consider a ray a beam passing through these materials, the total attenuation coefficient is going to be 5 because it's going to be 1, 2, 3, 4, 5 going up there. But the one that passes through the center, we're going to get 14 because there's 10 in the middle. But all the other ones are going to be 5. So this is what we're going to get. We're going to get a radiograph which sort of represents sort of the total attenuation coefficients that we've obtained. And after we rotate the sample, we can then add along the diagonals again, and this is what we get. And if we go along this direction, we obtain this here. And same thing if we collect in this direction from right to left, we get a similar sort of radiograph to what we got in this direction. So this is how we are collecting the radiographs actually. And so once we've collected the radiographs, now the back projection is what we want to do. So we've got the radiograph here with these attenuation coefficients. So this but of course, on the radiograph, what we're not, we are simply observing this grayscale image, right? And so what we can then back project. So we've got 5 here. We now want to see what does our sample look like? So we back project here. We've got 5. So we say, okay, we smear the 5 all along the way because there is no way of telling from here when we got the 5. We can't tell what this is. It could have been 5 here and 0, 0, or maybe half and something else. So we smear the 5 back in all of these, and so we've got the 14, 5, and 5, and we do the same in all the different directions. So this is sort of and once we've done for all of the different directions, and we've summed all the back projection data, we get this, but initially we had 1s and just a 10 in the middle, but now we have the 25, 26, but we still have a very high number in the middle. So this is a reasonably sort of good sort of reconstruction, if you can call it, but it's not perfect. So what we then do is if we normalize it, that makes it better, so that the average equals to that at the start, but then still we now have some variations here, which are not So great. Oh, so it's not exactly what we had at the beginning. So what does back projection do? It recreates the linear absorption coefficient distribution of the object with only one square in the middle of the sample having a high linear absorption coefficient value. That we've managed to do. So mathematically, back projection can be described by this formula here, where this mu of xy is the linear absorption coefficient value obtained for a simple back projection. But this is significantly different from what we had at the beginning, because the central peak of the linear absorption coefficient becomes lower and it's horizontally wider, and it is influenced by the surrounding areas with lower linear absorption coefficients during back projection, and ultimately this results in a blurred final image. So an image which shows only projection data from one direction. If we get projection data from 4 directions and accumulation of data from 10 directions, it starts getting better. But accumulation of data from about 400 directions, this is far better. So we can see that we have a magnetic cylinder and a polymer around it. But then because we've got the blurring, we can then apply a filter. So if we apply a Fourier transform on the projection data and then apply an inverse Fourier transform after this is filtered, then back projection becomes a final step that yields the original distribution of the linear distribution. Just to mention that there are quite a number of filters that are used for this filtration process, and so if someone is interested, we don't have the time. It would take maybe another lecture to just go through the filters that can be used. But for example, here, if we were to apply a ramp filter, for example, of this form, and that would be the equation, what you then or see is that if we apply that ramp filter to our data here, and we start and when we back project this, we're starting to get something that is better. And after a filter, this is a better representation of our original data. And after normalization, um, we now have something that is closer to what we got initially. So this is an example of what the filtered back projection algorithm looks like. So there are a number of filters that can be used. There's the RAM filter, the Ramachandran, Butterworth filter, Han, and many more. If you're interested, please just go and have a look at these filters. You can easily get lost in these things, and that's one area of study. Also, for most applications in proprietary reconstruction software, it usually comes with when you purchase a CT scanner, it usually comes already with a reconstruction software that already has filters that are preset that you can use. And one is only to try one and see if it is improving the data. But again, depending on your application, you might find yourself needing to sort of apply to sort of use a different reconstruction software, and that allows you some flexibility in adding something to the filters or other parts of the reconstruction software. And by the way, with the filtered back projection, then this is if you look at the magnetic cylinder again with a polymer around it, now with a filter, you see that you actually get much better reconstruction. Of course, this is only with 400 directions, and if you get even more directions, like 1,000 directions or 2,000, you will find that actually even the noise also decreases in these images. So once you've done the reconstruction of the data, then there's the data visualization that that needs to be done, because um, usually what you're doing is you're studying something, right? So if I go back to the example of the insect, maybe you're interested in the insect. Maybe you want to see if this insect, which existed, let's say 50 million years ago, maybe there were certain features that the modern day insects don't have in them. For example, maybe the the legs were bigger, or maybe it had more wings or something like that, or maybe it didn't have scales or whatever could be the difference. So you reconstruct and you get the 3D volume, and then now you need to look at the 3D volume and study it. And to study this 3D volume, there are several softwares that are available. Volume Graphics is one of them. Aviso is another one. Dragonfly is free if you want an academic license. If you're working on an academic project, ImageJ is completely free, and it comes with a lot of modules also for doing a lot of different things. For example, people working in paleontology might want to use BoneJ, so there's something that is made for it, and a lot of other sort of modules that have been added to to ImageJ and Fiji. So that's the first part of my presentation on the imaging bit. So what I'm going to do now is that I'm going to move on and talk about um, tychography, which is still um, X-ray imaging. So I'll start from here. Um, actually, um, so um, so with tychography, then, let's start with a lens. So a lens, what it does, it varies the speed of an oncoming wavefront to create a focus. So, for example, here we have a lens, and we've got our incoming wavefront, and it varies, and it creates a wavefront here. And so the resolution of the image formed by a lens, it's limited by its numerical aperture or collection angle, and manufacturing high numerical aperture lenses for X-rays is difficult, and it limits the resolution that you can get. And then so that's just because lenses, you then use them in the imaging process when you want to get higher resolution, right? But again, another component that you use in when you're doing imaging is the detector. So if you remember in the first part of my presentation, I was talking about phase contrast. But then when you look at how a detector works, because what generally happens is you get X-rays, they fall onto a scintillator material, which converts where they're absorbed, and the electron hole pairs are created, and and then you have some readout chips that then read the signal on the other side. I hope someone, I think in the previous lectures, there might have been a discussion on detectors. So. What that means is that we can only measure the intensity of X-ray photons arriving in a given pixel. The phase of the wave on the detector is lost. So we can't actually measure the phase directly on a detector. And then coherence. I think I'm going to skip this because so there's temporal coherence and spatial coherence, and I believe these have already been discussed in detail. So what? So in microscopy, then in X-ray microscopy, what you're doing is you've got your objects here. So this is depicted by this guy holding. Let's assume this is the object. So you get your photons, and then they are scattered from a sample based on its refractive index. And these X-rays, then the photons are then uh, you put an imaging lens that focuses the scattered photons onto an imaging plane over here. And the and we then record an exposure of the image. And because as I've already mentioned, the fabrication of the lenses, we can't you can't you get aberrations, and you can't get very high numerical aperture lenses. You get a good enough image, but it's not as good as you'd really want it to be. So that's the image, and that's the object that you have. So this is what happens in microscopy. So the different types of X-ray microscopies, like you get X-ray CT, you get transmission X-ray microscopy, and you get phase contrast CT as well. So that's the different microscopies. But then, so one technique that has been used is coherent diffraction imaging. So, sorry. So let's see. Yes. So what you could then do, because the lens because we are getting imperfections because of the lens. So if we what it happens if we then remove the lens, so that we have our X-rays coming in, we have our sample, and then after the sample, the X-rays are detected. We put our detector over there, and instead we replace the function of the lens with computational reconstruction. So on what we're detecting is we put it into the far field. Remember when I was showing you the effect of having the detector at different distances. I did mention that I'm going to talk about having the detector in the far field much later on. So this is when you have the detector in the far field, you don't get a radiograph that shows you sort of a shadow of the image, but you get this kind of image here. And so uh, um, uh, you then want to recover the relative phase of the image. You need to know what the image looks like of the sample, right? So um, this technique would then, because we've removed the lens, it should then allow us to recover both the modulus and the phase components of the wave, and it is not limited by the quality of the optical components. So it will give us a perfect transfer function. So here, for example, yeah, that's a computation. So we get our object, and we detect here, and after detection, we do some computation, and we should then recover an object that is a better representation of an image that is a better representation of the object. So how to then reconstruct? So here, so this is so what we're talking about is CDI, so coherent diffraction imaging. So what you do is you have your sample, and the sample is smaller than the size of the beam. So you want the sample to be completely illuminated by the beam. And so that's why we have this square here, and the white square in the middle, that would be the sample, and then around it is the area which is the footprint of the beam, right? And so what you're going to do is when you on your detector, you are going to get this diffraction pattern here. So if you then so that's so in the imaging part, in the coherent diffraction imaging, the requirements are that you need a coherent beam of X-rays, right? And of course you need the beam to be bigger than the sample. So what you know is that this diffraction pattern that you get here, it is actually a Fourier transform of your object and the beam. Um, so if you take or if you take your object and your beam, and you take a Fourier transform, that should give you the uh, the diffraction pattern that you get on your detector. But remember, we said on the detector we don't get the phase; we only get the modulus of the absorption image, right? So because of that, our our image is only going to have the modulus. So, but we don't know what our sample looks like, and we don't know what our beam looks like after doing the experiment. What we do know is what we detected on the information that we got from the detector. So what we do is then when you're doing CDI, is that you then start with an estimate of what the sample looks like, and you start and what the beam is like, and from there. You take a Fourier transform, but of course you've got the constraint that the sample has to be smaller than that, so you paired it with zeros, and you take a Fourier transform of that. And after taking the Fourier transform of that, you take the modulus, and the modulus then should then give you what you were supposed to get on your detector. But of course, because we've got an assumption initially, that is going to be different from what you got on your detector. So you update the image that you got. You update your estimate. You update the modulus, and after that you sort of update. You go back and you update. You do the inverse Fourier transform, and then you update the object, and you also update the beam, and you iterate until it converges to what you obtained on your sample on your detector. And so that's how the sort of coherent diffraction imaging works. So in the end, so here's the first demonstration of CDI. It was obtained in 1999. So these were gold dots that were fabricated, which are about 100 nanometers in diameter, and after sort of this is the phase, the absorption contrast image, and with 3DI, um, you manage to recover actually what the sample actually looks like here, as you can see in image C. So now coming to tychography, then uh, the tychography is an extension of coherent diffraction imaging, because tychography comes from the Greek word to fold, which refers to the overlap of interference between coherently illuminated adjacent break reflections. In tachography, coherent radiation is used, same as in CDI, and the transmitted signal is spatially resolved using an area detector. So with tachography, then this is what's happening. So this is our object again. So what we do in CDI, we have the sample needs to be smaller than the beam. But in tachography, the sample doesn't need to be smaller than the beam. What we then do is instead we scan through the sample and we make sure that the beam overlaps each time. So, for example, as you can see, if the red square is the beam and we're collecting this sort of these frames as we scan through the sample, making sure that there is an overlap, and when we're done, so as you can see, we've got all these overlaps. So you can see the features are represented, multiple features are represented in several images at the same time. And this is what we actually collect on our detector for each one of these positions. So once we, so this is an actual experiment at our beamline. So here we're scanning a Siemens star. As you can see, the beam moving around. So we use a Fresnel zone plate to focus the beams to about 5 microns size. And so that's the size of the beam that will be falling on the sample. And we scan sometimes 100 by 100 steps, so 100 steps across in X and 100 steps in Y, which means we collect quite a lot of frames in the end. If you can imagine, just to obtain one projection, you're collecting something like 10,000 frames. So this is what you're recording on your detector. And then this is, of course, the reconstruction that you then do, the overlap that you can see that over here in this image. And when you're finished collecting the images, what you observe is that you can then get very high resolution, like under 50 nanometer resolution for your images. So basically, then when you're doing tychography, what you're doing is now the constraint is in the overlap, but you collect projections around and then you reconstruct for to get one projection. So if you have a very thin sample, for example, if you have some thin sort of brain tissue that you want to image, then you just scan in 2D and you get a 2D image. And for that, that 2D image may be sufficient for to get all the information that is required by the researcher to do the analysis that is required. But however, if it is required to get a 3D image, then after doing that 2D scan, you then rotate the sample and then you collect another 2D scan and you rotate and you collect another 2D scan. So as you can imagine, the technique takes a long time to do because to do one sample in 3D because you have to rotate the sample and collect 10,000 frames each time. So typically at our beamline, this can take something like 8 hours, depending on the size of the sample. But however, if you look at the papers that have been produced at our beamline, I think last year we managed to get the fastest scan, tachography 3D scan at our beamline by optimizing the motor movements. So you get advantages of doing tachography. You get resolutions of tens of nanometers. The field of view is about 100 microns at our beamline in 2D, hundreds of microns, high sensitivity to phase changes and electron density. The reconstruction, we usually use this a tachographic iterative engine. So again, we've got a beam and we've got the object, but we don't know what the beam looks like and we don't know what the object looks like. So we start with an estimate of the two of the object and the beam. So these are the estimates of the object and the beam, and then you do a fast Fourier transform, and so you've got your exit wave and you do the fast Fourier transform, it gives you that, and then you take the modulus of that, you find the intensity, the modulus, and you compare that with what you actually obtained on your on your detector, and then you update. And after updating, sorry, I'm going in the wrong direction. After updating, this is the updated function. You do the inverse Fourier transform, and you then update the object, update the probe, and so you now sort of after updating, you now have sort of a better sort of estimate of that, and then you put it back in to you put those estimates in, and so you iterate sort of maybe sometimes 200 times, and eventually you get your probe, which is the beam that was on the sample, and the object. The advantage of this is that the model can be extended to allow for further experimental uncertainties and properties such as scan position, misalignments, partial coherence, and it's a robust method. It can be adapted to many instruments and also several geometries. Yeah. I'm going to skip this, and just about the data collection. So the sample is scanned through the beam in a 2D grid with a 2D detector frame recorded at each position. So here, for example, if that's our sample, you scan around as I've shown before. Uh, so you have to determine things like how much exposure and how much overlap you need for when you're doing the scanning. And typically scanning with a step size of about 0.2, 0.3 of the beam diameter. And 4D data contains all of the required information, reconstruction required to invert the data. The time for collection and reconstruction, as I've already mentioned. So for collection, it can take about 8 hours, but then the reconstruction, it also takes a long time. So if you can imagine, if you collect for each projection, you're collecting 10,000 frames, 100 steps by 100 steps, for example, right? And then you collect, if you do this in 3D, so you are rotating the sample and collecting, let's say, 1,000 projections. So that becomes 10,000 times 1,000. And so the time to just reconstruct um, all the projections, and then after that, after you've reconstructed the projections, you then need to reconstruct. You then use tomographic methods like the filtered back projection to then reconstruct the 3D image. And then only after that you can then go to Aviso or to ImageJ and then do analysis of your sample and look at the data. So I work at I-13 at the I-13 beamline at the Diamond Light Source in the United Kingdom. And this is what the beamline looks like. We've got two beamlines actually in the same building. It's an external beamline. So this is inside the ring. This is where inside the ring. So we've got our angulators inside the ring, and then we've got the beam is produced over here, and uh, it comes through here, and this is our optics hatch where we have the monochromator, and after passing through the optics hatch, we get into the experimental hatch where we've got some slits, a sample stage, and we've got a tachography detector, which we can move the sample to detector distance. We can get up to a maximum of 15 meters away from the sample. We are right next to the I-13-2 beamline, which is the Diamond Manchester imaging beamline. Also, where they do here they do phase contrast tomography, high resolution phase contrast tomography also. So applications, I can see that I don't have a lot of time, so I'm going to sort of try to uh, to skip over some of the applications. Applications of tychography then. So for example, if you um, uh, you can use the polarization of the X-rays then to look at the magnetic domain imaging in a material. If you can look at this paper, for example, by Claire Donnelly, who's done quite a lot of work on this magnetic domain imaging using tychography. You can also look at electronic science. You can look at ICs because of the high resolution that we can obtain. You can then study these ICs and look and do non-destructive imaging. And look at the different components and if there are defects in them. Then another thing that you can look at is you can look at batteries. So, for example, quantitative evaluation and nickel-rich cathode and a nickel-rich cathode particle here. So, for example, you're looking at a pristine material, and then when it's charged, you can see actually the changes in the morphology here. As you charge the battery. So these are some of the applications that some of the users have used at our beamline, because with tychography also, because what you're doing is essentially you also reconstruct the beam, right? So you can then use it actually to study optics. Optic features. So here is an example of work that was done to study optic features. So you can, because you reconstruct what the beam looks like, and then you can back propagate it, and then you can look at what your optical features look, how your optical features are performing, and you can make adjustments and look at the defects in these and aberrations in your optics, and also study them. There has been also some work on sort of looking at magma particles, where, for example, here figures A and B, they show volume renderings where only these nanolites, which are the magma particles, which occur as spherical isolated crystals as well as more irregular shaped aggregates, and C and D show renderings where also they show that they have got depleted glass around between nanolites, which is segmented in yellow. So these are these are sort of examples, the variations of research areas that you can look at. We've had some people looking at silk fibers, for example, looking at the morphology at high resolution, where you can see actually whether they are porous or not in here. Um, yeah, they are also, for example, butterfly scales. Just to mention here that we've had some work. So you can see that here these butterfly scales have got a periodic structure on the scales. So we've worked with Holderid, who is from the University of Bristol, and said he came with he brought some moth scales, and with these moth scales, what after doing tychography on them, you do the imaging. What you find is that they also have a periodic structure, but the periodic structure that you have on those moth scales, um, you find that they because of that periodic structure, ref, within a certain frequency range, they don't reflect sound. They only reflect sound in other frequencies, but not within a certain frequency range because of that of that periodic structure of the scales. And it so happens that that the frequency range in which they do not reflect acoustic waves is the same frequency range that is used by bats when they're locating they're figuring out their surroundings, because they send acoustic waves and then they're reflected back. But now, because of these moth scales, they're actually not seen by the bats, and so they're not eaten by the bats. And so that's one of the interesting sort of outcomes from we're using tychography and X-ray CT imaging here at the diamond light source. So that's some of the interesting work. So why is tychography so appealing? Well, it's because we get a nanoscale resolution, um, sensitive to small changes in electron density, and it's quantitative also because we can quantify. I should mention that when we get phase contrast with tychography, because remember I was when I was showing those spheres and the first part of my presentation, and I was talking about the distance, right, where you put the detector a little bit further away, and then you start getting phase contrast, where you start getting these phase fringes. But that's inline phase contrast, and with inline phase contrast, it's sort of in the one radiograph, you've got absorption contrast and phase contrast in them. But with psychography, because of the reconstruction methods, you can actually get a phase contrast a phase contrast image, a phase image separated from the absorption contrast image, so that you can completely separate them. And that's why we're saying it's more quantitative, and it's also sensitive to small changes in electron density. And then many synchrotrons around the world are upgrading to a diffraction limited ring, so that would mean that it becomes more possible actually to do uh, uh, tychography with higher coherence and also higher flux. Another sort of major advantage of why tychography is appealing is when you're looking at soft tissue, because with soft tissue, one of the things that you want to avoid is to damage the material. Um, um, because you don't want to apply too much X-ray dose onto your soft tissue. So with X-ray tychography, it allows for low dose imaging, but also with high resolution at the same time. So, for example, here you're seeing a reconstruction of brain tissue, and here, this is what it looks like at 3 microns with absorption contrast. But with phase contrast, you can actually start to see some of the neurons here in the reconstructed image. And here, this is a lung tissue where you can actually see some of the asbestos inside the lung tissue. over there and in high resolution. So thank you very much. I think I've left enough time for questions, if there are any questions.
Yeah, I think thank you very much. Thank you for the nice talk, nice presentation. Yes, there is enough time for questions, and there are indeed questions. So the first is by Sonia Utterman, and she asks, is ptychography fast enough for operando measuring of ICs?
Ah, um, of ICs. ICs, I don't, what does IC mean? Integrated circuits?
Um, I suppose so, Sonia.
Um,
Yes,
uh,
exactly. Yes, integrated
uh,
circuits. Yes.
Integrated circuits.
Yeah.
Okay, so I think what I would say is that tychography, the short answer is tychography is not yet fast enough. It's a very slow technique. Um, if you're looking only at radiographs, maybe, but you see, the thing is, um, you have to play around in order to get the contrast that you require. You play around with exposure. So one radiograph can take about a minute or 2 minutes just to acquire, and that might be too long for operando. Um, Measurements, even if you want to just do sort of 2D measurements. But if for 3D measurements, I would say definitely not. What we have done operando experiments before, but they have been with batteries. And what has been happening is that the operando case is that you mount the sample on the sample stage, and you do a 3D tychography, and then after that, without removing the sample, they put the electrodes, and they charge and discharge maybe 1,000 cycles, remove the connections, and then do another tychography until they start seeing cracks. So but it's not fast. It takes 8 hours to get a 3D image. And even after acquiring the data, the amount of time that it takes for you to actually see what you acquired, sometimes it's a week because yeah, so it's still in development. Yeah.
Okay, thank you. So the
Yeah.
next question is by Zahid Mushtaq. So please unmute.
Okay, thank you again, and very informative presentation again. My question is, how are filters typically handled in commercial CD scanners software from a user perspective?
Uh, how are filters handled? Is that the
Filter,
question?
yes.
I'm assuming you're talking about X-ray filters, right?
Yes. Yes.
Okay. So filters typically at a synchrotron. We had filters at the ESRF when I was at the ESRF working at BM5, and you typically put the different materials on motorized in a vessel where they are motorized, and you decide, um, and then you sort of the beamline scientists then commission them and look at the different energies that you get with the different combinations of filters. And so that when users come, they don't need to do this again. You just know if they want to get 90 kV, then we need to use these filters. So I they are generally put into the beamline and on motorized stages and commissioned well before. I don't know if that answers your question.
My question was, I just wanted to know about the filters used uh, in
For
CD
for
scanner from a user's perspective.
Okay, in a CT scanner, so you'd usually have something like copper. We had molybdenum. We had um, it was usually a combination of different thicknesses of copper and molybdenum and other metals usually, and you just put in a combination that works for you.
Okay,
Um,
thank you.
yeah.
Thank you. So the next question is by Ahmed Dawalbait. So please unmute.
Thank you very much for this nice presentation. Do you hear me?
Yes, I can
Yes,
hear
very
you.
well.
Okay, thank you very much for this nice presentation. And my question is, can I use this technique for semicrystalline polymeric materials? And the next question is, can I use it for nanocomposite? Because nanocomposite is organic and inorganic uh, uh, composite materials.
For nanocrystals, uh, the question is, do you want to observe the crystals
I have two
or?
questions. I have two questions.
Yeah.
First one is for semicrystalline polymeric materials. If I want to observe these small voids and also fibrils inside, I want to show this how these molecules are aligned.
Yes. So for fiber composites, definitely, and for composite materials, yes. These techniques are depending on the size of your sample and the size of porosity or size of materials that you want to look at. That determines the resolution, and that can then determine the technique. You can either use X-ray CT, or you can then go to tychography. Either of the two. But for nanocrystals, if you want to see individual crystals, no, I don't think you can. What you could do is at our beamline, we also have this technique called Bragg coherent diffraction imaging. And with this break, you then do it in reflection mode, and then you can look at the reflections from each from a crystal and sort of determine the stresses in the material. But I decided not to include that for my presentation today. But for to see nanocrystals, if you've got a homogeneous material which is just crystalline, and you want to see the crystals, I don't think this is the best technique. You'd probably not
No,
know.
I mean that I don't want to see the crystalline, but I want to see inside this crystal. Because for polymers, it has
Uh-huh.
the molecules, and these molecules are as long as it's like these molecules. It's linked between the links between these molecules is hydrogen bonds. Like for polyamide, for nylons, or for polyethylene, these are molecules. If I want to see the fibrils inside, sometimes there is a fibrils, there is some fractures. Also, there
yes.
are
Okay,
some
yes.
voids.
Yeah, yes, you can. Yes, you can. Definitely, you can see the voids, you can see the fibrils, and you can see the cracks.
Okay, thank you very much. Thank you very
No
much.
problem.
Thank you. Are there any further questions? I don't see any. So thank you, Kudakwashe, for the nice presentation. Very, very nice. Thank you.
Thank you
And
very much.
thank also to all the other speakers. So I